Welcome to Stats Master Screencast. We are BTech Quality Stats 3 class in Cape Peninsula University of Technology. The members of this group is Zenande Gobeni, Saneliso Mangisa, Masekole Mgodeli, and Bulelani Vumazonke. Our intentions with this screencast is to give a relationship between probability and normal distribution. To simplify things, we will explain probability as well as normal distribution. And we will link the two, and later on we'll discuss an example that will help us to understand the relationship between the two. And in conclusion, we'll answer two questions. One will be where Z-scores can be used in quality management. And the second one is what does that have to do with quality management? Let's define probability. Probability is a likelihood that an event will occur. Usually it is expressed in numbers between 0 and 1. If probability is 0, then certainly no event will occur. Nothing will happen. There's no chance of something happening. Whereas if probability is 1, then certainly an event will occur. Something will definitely occur. Normal distribution is described as a theoretical distribution of values. So from a collected data, that data can be normally distributed. But to simplify that, let's use a picture which gives us a curve of a normal distribution. So in this curve, there's a center line in the curve. And in that center line, the mean, the mode, and the median, they are all equal in the center line of the curve. As you can see, the shape of the curve is a bell-shaped curve because it forms a shape of a bell. And also in this curve, the width of this curve, that is from -3 standard deviation to +3 standard deviation, is determined by a standard deviation. So if the standard deviation is small, then the width of the curve will be narrower. Whereas if standard deviation value is bigger, then the width will be wide. There's also what is called an empirical rule, which is 68-95-99.7 rule. What does this rule mean? It means between 1 standard deviation plus 1 standard deviation and -1 standard deviation, 68.27% of data lies in this area. Whereas if you go to -2 standard deviation and to +2 standard deviation, that means 95.45% of data lies between the -2 and 2 standard deviation. And between -3 and +3 standard deviation, 99.73% of data lies in that area. So under the entire area of the curve, we've got 100%. And to be exact, it's 99.73%, and the other 0.27, that is the outliers. So in other words, we can translate that to say under the entire curve, probability is equivalent to 1. What else do we need to know about normal distribution? In normal distribution, is that it's wholly based on probabilities, because there's always a possibility of an error. To get a probability of an occurrence of a randomly distributed variable, then the Z-scores are used. So simply Z-scores, that is the number of standard deviations from the mean of a data point. But more technically, it's a measure of how many standard deviations below or above the population mean a raw score is. And we use a formula which is Z equals to X value, which is the raw score, minus mean divided by standard deviation. So from the collected data, we can take any value from that data and transform it into a Z-score. So in order for us to do that, we need to have a raw score, that is an X value. We need to have the mean, and we need to have standard deviation. And once we've got that, we get a Z value. And for us to interpret that to probability, we use a standard normal table. which is a table like this. So in this table, it tells us the Z value based on our calculation. So that's how we calculate Z-scores from our data. But let's make an example to simplify this content. We've got watermelons harvested that have an average weight of 2.25 kilograms and a standard deviation of 0.4826 with specification limits of 1.5 kilograms and 3 kilograms on the upper spec limit. The question is, what is the probability of selecting randomly a watermelon weighing more than 2.5 kilograms? So we're looking for value more than 2.5 kilograms. So let's look at our data in order for us to do a calculation. So we've got a data that's collected with a total of 50 watermelons that have been weighed. So we're going to use this data to determine probability of selecting a watermelon that weighs more than 2.5 kilograms. So from this data, we'll certainly get a curve that looks like this. So this curve represents the data that has been collected with the mean at 2.25. Let's quickly look at this data. So we need to know the mean in order for us to calculate the Z-scores. Let's work out the mean. So we'll say equals to average. So average would be data selected, or the total 50 points of data. We'll need that. And then that gives us 2.25. That's our mean. And then let's work out our standard deviation. We would say equals to standard deviation. Then we select the data that we need for that calculation. And that gives us a value of 0.4826. Now from that, we can now calculate 3 standard deviations, because on either side of the curve there's 3 standard deviations. So our Z-scores would range between or from minus 3 standard deviations to plus 3 standard deviations. So we'll say equals to 3 multiplied by the standard deviation of 0.4826. Then we get a value of 1.4479. Now let's calculate quickly the USPL, that is the upper spread limit. In order for us to do that, we would say equals to the mean plus the 3 standard deviation value, and that gives us our upper spread limit. Let's narrow that down to 4 decimal places. We'll do the same for lower spec limit. So I would say equals to the mean minus, because it's on the left hand side of the mean or below the mean, minus the 3 standard deviations. And there, let's take it down to 4 decimal places. We get 0.8018. Now let's go to our calculation now and check what is the Z value. So we are given the mean of 2.25 kilos. We're given standard deviation of 0.4826, and we've also proven that on our calculation. So we're going to use those values to determine Z value. So I would say equals to, open brackets, value of 2.5 minus the mean of 2.25, close brackets. We divide that by standard deviation, and we get a value of 0.52. So the Z value is 0.52. Now we go to our standard normal table and look at where is 0.52. So we can see 0.5 on the left column, and on the top row we can see where 0.2 is. So 0.52 will be at 0.1985. So that is our probability. So 0.1985 is our probability. That's the likelihood of occurrence. But that 0.1985, what does it mean? What does it tell us? This basically tells us that our Z value that we've just calculated gives a probability between the mean and 2.5 kilograms. But we're keen on this area here. We want to know the value of probability from 2.5 kilos and above. That's where our interest is. So let's carry on with our calculations in order for us to determine that. So now we're gonna calculate the upper spread limit and then figure out what is the probability from 2.5 kilos and above. So let's say equals to, open brackets, we go to our USPL, we minus our mean, close brackets, we divide that by standard deviation. Okay, let's correct that should be the mean there, 2.25, close brackets, divide by standard deviation, we get a value of 3. So again, we go to our standard normal table, we'll look for the Z value of 3. Let's see what that is. There we get 0.4987. So 0.4987, that is our probability. So now, in order for us to determine the probability, as the question was saying, let's look at our question. So the question says probability of selecting randomly a watermelon weighing more than 2.5 kilos. So there, we will then take the difference of the two, we will say equals to 0.4987 minus 0.1985. Then we get a Z value of 0.3002. So that Z value gives us a probability of selecting a sample weighing more than 2.5 kilograms. So our Z-score percent in that area will be 19.85%, and on this area it will be 49.87%. We just multiply the Z value by 100. Same applies here. We've got probability of 0.3, so that will become 30.02%. So that means the probability of selecting a watermelon weighing from 0.25 weighing 2.5 kilos and above will be 0.3002, which translates to 30.02%. So 30.02% of our data lies in that region, which is from 2.5 kilograms and above. In conclusion, where can Z-scores be used in quality management? So in quality management, Z-scores are useful to compare results from a sample to a population. Test results have many possible results and units. However, those results can often seem meaningless. For example, knowing that a watermelon weighs 2.5 kilograms might be good information. But if you want to compare it to the average watermelon weight, looking at the vast table of data can be overwhelming. Now, a Z-score can tell you where that watermelon weight is compared to the average watermelon mean weight. So what does that have to do with a probability? Variation is the enemy of quality. Therefore, knowing a probability of some sort in a normal distribution helps to improve and reduce variation in a process. Attributes. We would like to thank CPUT for this presentation template and also the Creative Commons license that we've given, and also we send our attribute to Howard's Data Science for the image we've used for our normal distribution curve. Thank you.